So what I've done in my paper is try to start from a point of view where you don't assume gravity to be there. You would like to explain it by seeing how you can derive it from a more microscopic set of equations where gravity itself is not assumed, but then just follows from a certain logical reasoning. So taking gravity into account then gives us a bit of a problem, because then we have to talk about space-time, and then these quantum uncertainties gives us another way of looking at space-time at the short distances. So this led to problems, and string theory is another way of also looking at gravity and quantum mechanics, which I've been working on quite a bit. So people have studied the problem of quantum mechanics and gravity from various perspectives, from string theory, but also by thinking, for instance, about black holes, what happens with black holes. And I've taken some of the things we've learned about it and seen that there is some explanation of maybe where gravity then comes from those new way of thinking about quantum mechanics and gravity together. So if you then start trying to explain where it comes from, it has to do with the fact that there's, at a microscopic scale, a certain information about how you describe this, which we don't see ourselves. We forget about that. And it turns out that if you take that into account in some appropriate way, that you can understand where gravity comes from. It's fun to think about things like gravity and even, well, what I had in my paper, things like even the laws of Newton, because they do play a role in one's everyday life. But it's surprising that when I go and walk out the door and something like that, it's not like I immediately sort of think about these things in a different way. But for me, I think it's more important eventually what will be the implications for understanding not just gravity, but also what's happening in the universe. I mean, the gravity equations of Einstein are also used in describing the expansion of the universe. The Big Bang theory are all based on these same equations. What I hope is that the ideas that we are now starting to develop for gravity can eventually sort of lead to possibly somewhat better or even more refined way of thinking about the early universe. And I think that will influence a little bit more my thinking than, I think as human beings we like to know where we come from and how the universe sort of developed into what it's now. And there I think eventually this will have some impact. Yeah.
Quantum gravity, a central and ongoing challenge in the realm of theoretical physics, represents a profound quest to reconcile two of the most fundamental and successful theories in the field: general relativity and quantum mechanics. General relativity, initially formulated by the visionary physicist Albert Einstein, presents a strikingly elegant framework that illuminates the workings of gravity. It describes gravity not as a force, as depicted by Isaac Newton, but rather as the curvature of space-time induced by massive objects. This remarkable insight revolutionized our understanding of gravity, providing a beautiful geometric description of the cosmos. In stark contrast to general relativity's cosmic perspective, quantum mechanics reigns as the foundation of particle physics, governing the behavior of particles at the quantum level. Quantum mechanics introduces a multitude of intriguing and counterintuitive concepts, including superposition, uncertainty, and quantization. It offers a probabilistic view of the universe, where particles can exist in multiple states simultaneously, and their properties cannot be precisely determined at the same time, a stark departure from the deterministic world of classical physics. The crux of the matter emerges when we endeavor to merge these two pillars of modern physics in settings that defy our everyday experiences. Consider, for instance, the environment around a black hole, where the gravitational field is incredibly intense. According to general relativity, black holes are regions of spacetime where gravity is so overpowering that nothing, not even light, can escape their clutches. However, When we venture to describe the behaviors of fundamental particles near a black hole using quantum mechanics, we confront profound challenges. Quantum mechanics introduces the notion that particles cannot be precisely localized, which collides with the precision in determining particle positions predicted by general relativity in the vicinity of a black hole. This inherent conflict is at the heart of the quest for a theory of quantum gravity. Critiques and challenges abound in the realm of quantum gravity. Incompatibility between general relativity and quantum mechanics. The foremost critique revolves around the foundational challenge of reconciling general relativity's conception of a smooth, continuous spacetime, characterized by graceful curvature, with the discrete, probabilistic, and granular nature of quantum mechanics. The pursuit of a unified framework capable of harmonizing these two disparate views stands as a monumental endeavor. Lack of empirical evidence. A notable concern is the paucity of empirical validation for quantum gravity concepts and theories. Many of the concepts put forth, including string theory and loop quantum gravity, have yet to receive direct experimental confirmation. The absence of empirical support places quantum gravity on precarious ground within the scientific community. The problem of non-renormalizability. A significant technical challenge in the context of quantum gravity is the problem of non-renormalizability. This term signifies that when attempts are made to perform calculations, especially in situations where quantum effects are prominent, mathematical infinities emerge that defy easy removal or management through the process of renormalization. This challenge poses a formidable barrier to consistently describing quantum gravitational effects mathematically. Among the prominent approaches to quantum gravity, string theory and loop quantum gravity have earned recognition. String theory, a highly theoretical framework, suggests that the fundamental constituents of the universe are not particles but rather tiny vibrating strings. These strings vibrate at different frequencies, giving rise to various particles and forces, with the aspiration of unifying all fundamental forces, including gravity and quantum mechanics. String theory, however, grapples with the challenge of empirical verification, remaining largely speculative. Loop quantum gravity, on the other hand, introduces a distinctive perspective. It posits that space itself is not continuous but composed of minuscule, discrete units, which form an intricate network or loop of interconnected nodes. This network provides a foundational framework for comprehending the quantum properties of gravity. Loop quantum gravity has made notable strides in elucidating the behavior of matter in strong gravitational fields, particularly in the vicinity of black holes. Nevertheless, it continues to be a subject of active research and refinement. Recent theories have emerged to challenge conventional paradigms and offer fresh perspectives. One of the most notable is the emergent gravity theory put forth by the distinguished theoretical physicist Eric Verlinde. This theory introduces a departure from the traditional view of gravity as a fundamental force. Verlinde suggests that gravity may not be a fundamental aspect of the universe but rather an emergent phenomenon that arises from changes in the microscopic structure of spacetime. In essence, this theory reframes gravity as a consequence of the interactions and alterations of more fundamental constituents, challenging the need for it to be a fundamental force. A crucial implication of Verlinde's theory is its potential to obviate the requirement for dark matter, a mysterious form of matter believed to make up a significant portion of the universe's mass, inferred from its gravitational effects. By recasting gravity as an emergent phenomenon, Verlinde offers an alternative explanation for phenomena such as the observed motions of galaxies, which have traditionally been attributed to the presence of dark matter. This could have profound implications for our understanding of the cosmos. The relentless pursuit of reconciling general relativity with quantum mechanics continues to be a driving force in the realm of theoretical physics. As physicists actively explore diverse avenues and contemplate alternative theories, the field of quantum gravity remains dynamic and ever-evolving. These alternative theories present promising new directions, but they all share a common need for rigorous empirical validation. The potential for transformative scientific breakthroughs in this quest is profound. Such breakthroughs could not only reshape our understanding of the fundamental forces that govern the universe but also touch upon the very fabric of reality itself. The impact of theories like Eric Verlinde's emergent gravity extends beyond mere reinterpretations of gravity, and the existence of dark matter. It opens up new avenues for exploration in the realm of theoretical physics, promising to unlock the mysteries of the cosmos in ways we may have never imagined. The relentless pursuit of a unified theory of quantum gravity is a testament to human curiosity and the unyielding drive to comprehend the mysteries of the universe. It is a journey that challenges our understanding of space, time, and matter, and it holds the potential to revolutionize our perception of the cosmos. As we delve deeper into this intellectual odyssey, we may find ourselves on the cusp of a scientific revolution that could forever change the way we view the universe and our place within it. Thank you for watching another episode of Elizib. While you are still here, don't forget to like and subscribe.